Hello everyone, welcome to video 17. The focus of this video will be on the law of sines and the law of cosines. Both of these laws should be familiar from when you took geometry, and we're looking at triangles in that class and then using sine and cosine basically there. Now, I bring it up here because we're going to use this essentially as kind of a review, but also in terms of looking at a new case for the law of sines, which is called the ambiguous case. But also looking at some applications, which I won't do in this video to keep it from being like super long, and instead saving it as the project assessment. So you won't really have a lot of problems to look at from me directly. The goal with that is, again, giving you a chance to research into this, to take that next inquiry step into seeing how the law of sines and law of cosines can be applied to some more difficult problems, and also some problems that I think are interesting. So I highly encourage you to definitely check out the project assessment for this, because it'll look really difficult on the forefront, but will also really help you in later classes, etc. And also will help kind of excuse me, not exemplify, like that's not the right word, but at least kind of showcase like how they can, how they can be used in vectors. So again, I would highly kind of encourage it for that sense, to look at it. Now, that's the goals here. So first off, we're just going to kind of review law of sines and law of cosines. We'll start with law of sines. And the goal is to essentially be able to solve non-right triangles. So essentially, if I had a triangle ABC and it was a non-right triangle, so I'm just going to draw kind of an arbitrary triangle here. So something like this. The capital letters are going to reference the angles located at each vertex here. And the way that I labeled this in terms of going ABC and going clockwise is just a choice that I made. You can technically label this however you want to. Definitely, you can label this however you want to if the angles aren't necessarily given. Obviously, if the angles are then given in terms of numbers, then we want to make sure we have it in the right spot. Same thing if they sketch a triangle out for us. Now, when we do something like this, it's really important to know then that for this, that for this angle here, the side opposite of it is related, right? Because what this essentially means is that the smaller the angle for A, then the smaller that side opposite would be. Think about it like a mouth, or if you were to put your palms together and put a rubber band in between your fingers, and then the wider that you open, the more stretched out that rubber band will be. And so that's why the way that the labeling then works is we use the lowercase letters to represent the side that corresponds to its angle. So therefore, little a will always be across from big A, little b across from big B, little c across from big C. And when we're solving these non-right triangles, notice then that there are a total of 6 measurements that we can find, right? There are 3 angles and there are 3 sides, 3 capital letters and 3 lowercase. Now, when I'm going through and I'm trying to solve for a triangle, what the directions are trying to get me to do is to find any missing measurements. Another way you can kind of think about it is I should be able to find all 6 pieces of information. Now, in order to do this, we need to be given at least 3 of these measurements in some kind of combination. Now, it's the combination that we're given that'll actually dictate if we use law of sines, law of cosines, or if I can't even solve it to begin with. All right, so starting with law of sines, given that general triangle here, with ABC and lowercase abc being the angles and sides respectively, what the law of sines states is it says that sine of angle A divided by little a, so this ratio between an angle and the side opposite of it, is equal to the sine of angle B over little b. In other words, when I take these two ratios, this ratio will always be equivalent. And this is actually true no matter if you were to do a non-right triangle versus a right triangle. So this is true just for triangles in general. Well, it's also true that if I set up the ratio with sine of C over little c, this would be equal to any of the other 2. And so this is called the law of sines. Now, sometimes I didn't put this in the notes, but sometimes you will actually see the law of sines written like this. In other words, they reciprocate each ratio. You can write it however you want. Both laws essentially say the same thing. One is easier to solve for the side. One is easier to solve for the angle. It really just kind of depends on what you're looking for. I think it's just easier to see and easier to write out the first way, and so that's what I'm going to use in terms of doing this. Now, another thing I'm not going to do in this lesson that I've done in previous pre-calc classes, especially at Mount Vernon, is we actually prove where this comes from. So I'm not going to do that. If you were interested in how these ratios are equivalent, let me know. I'd be more than happy to walk you through that during a virtual class or office hours, or share the CPM lesson with you. Otherwise, we're going to go straight into just using the ratios. So I essentially have our first example here. Let's solve the following triangles for all missing measurements. You'll notice that these two triangles, there are no labels. So just looking at A, let me go through. I'm just going to call this A, B, and C. And so if I was just to think about what am I given, I'm given angle A, which is 74 degrees. I don't know angle B. Angle C is 39. Little a, I have no idea. Little b, I do know. Little c, I do not know, right? Because this would be little c and this would be little a. So if I'm looking at these pieces here, I actually cannot use law of sines right now, because notice, if I'm going to go through and solve for something, that means I need to take a ratio, and I would need to know everything but one single item. So for example, I would need to know this angle, and this side, and then I could solve for little a. Or maybe I know this side, this angle, and this side, and then I could solve for angle B. No matter which way we do this, notice I have to at least know a pair, right? I need to know angle A with its opposite side, or I need to know angle B and its opposite side. And that's what kind of dictates the triangles that we are allowed to use law of sines for. It's that I have to be able to pair up or know those two pieces. And here I don't, right? If I have angle A, I don't have its side. I don't know angle B, but I know its side. I don't know angle C, but I don't know its side. So before I can even do law of sines, I need to see, is there a fact about triangles that will allow me to find one of these missing pieces before using the law? Well, there is, right? In a triangle, I know that all angles must sum to 180 degrees, right? That is a fact of every single triangle. So if that's the case, if angle A is 74, then I can take that from 180. And if C is 39, I can take that from 180. Then this should give me B. Right, so doing the subtraction, 180 minus 74 is going to be 106, minus 39. This is going to be 67 degrees. And here is my angle for B. This means now that I know B and little b, I can go through and solve for little a and little c using the law of sines. So that's the goal now. All right, so I'm going to set it up. So sine of angle B is 67 over little b, which is 17. This is going to be equal to, let's find little a first, sine of 74 over little a. And now I'm going to solve for little a. Now, this technique you've seen before. Think about here, this is a ratio equal to another ratio, aka it's a proportion, right? And how do I solve proportions? Well, to solve a proportion, we cross multiply. That's the key, right? So I'm going to go through and cross multiply. So this would be a times sine of 67. This is equal to 17 times sine of 74. And then I'm going to divide by sine of 67. Now, Now notice I have not gone through and actually found 17 times sine of 74 because I want to type this all in the calculator at the very end. So that way I don't have any rounding mistakes. All right, now when you type all this into your calculator, make sure your calculator is in degrees. And then again, we can just type this straight up. And what you'll get if we round to the second decimal place is 18.18. We can even state that this could be rounded to 18.2 if we want to round to the nearest tenth. All right, now there's my little a. So now I have one more piece of information we need to find, which is little c. And we're going to go through and use law of sines again. Now, I cannot do Pythagorean, right? Pythagorean only applies to right triangles, and this is a non-right triangle. there's no angle here that is equal to 90. All right, so I have to use law of sines again. Now, when I use law of sines, the goal is to always use the given information. So in other words, I know b is exactly 67, and I know little b is exactly 17. So I only want to use those numbers as much as I can and not try to use any kind of numbers that we've rounded. So in other words, I would not use the ratio sine of angle A over little a to help me find c. Right? I want to go back and always use the same starting ratio. So then over here, I'll have sine of angle C, which was 39. And I'm going to divide this by little c, and we're going to solve this just like we did with A. I'm going to cross multiply. This is equal to 17 times sine of 39. And then C is going to be 17 sine of 39 divided by sine of 67. Again, using a calculator, and I'm just going to round to the nearest, hundredth place. Then I would get 11.90 or 11.9. And now I have solved this triangle. All right, so let's look at B now. So I've got B already kind of sketched out down here and ready to go. All right, so notice this time I'm going to go through and kind of label it out. I don't have little a, I don't have little b. Now, just like last time, I'm given two angles, which means I can find the third. So I can actually find angle B, which is really, really nice because, again, this means I don't have to go through and use law of sines or law of cosines to find every single thing. So in this kind of case here, angle B is going to be 180 minus 80 minus 43. 180 minus 80 is 100. Minus 43 is 57. So there's my B. And then I'm going to use law of sines here, specifically doing sine of angle C, which is 80, over little c, which is 13. And I'm going to use this ratio each time to solve for my other missing two sides. Let's go through and solve for little b since we just found its angle. So this would be 57, sorry about that writing, over little b. To solve for b, we're going to cross multiply. So notice the same kind of process here. Very repetitious. Just kind of take your time and just be careful so you don't make any algebra mistakes. Again, you're going to be tempted to try to find all these numbers and round them early. Try to refrain from doing that. Do it all at the end. So typing this all into the calculator at this moment, you would get B is 11.07. Again, rounding to the nearest hundredth for right now. Use law of sines again. Again, I'm going to set up the initial ratio, sine of 80 over 13. This is equal to sine of angle A over little a. So I'm going to cross multiply. It's equal to 13 times sine of 43. And then A is 13 sine of 43 divided by sine of 80. Dang it, sorry. It's just nasty looking. And again, we're going to have to round this. So I'm going to round this to the nearest hundredth, and I get 9.00. There's my A there. So if we wanted to round to nearest whole numbers, honestly, in this kind of problem, because we have two significant figures here, we could do sig figs if we really wanted to. We could say that this answer is 11. And so I would actually just write it like that. And then we could say this answer is 9.0 if we really wanted to. But this would be fine. We're not going to worry too much about sig figs here, just because this is a generalization and not an application problem. If this was an application problem, then we want to be really specific in terms of how we're measuring. Because, again, if we were measuring in terms of miles, 0.1 of a mile is very different than 0.01 or 0.8 of a mile in terms of rounding. So we just want to be really careful with those distances. All right, so I want to introduce then this problem, which is called the law of sines, which is the ambiguous case. Now, in the previous two examples that we saw, we knew at least two of the angles, meaning we could always find the third by doing the law of triangles that all angles have to sum to 180. Now, a lot of the times this isn't the case. So what if I only know one angle and I know two sides? Then is it still possible to use the law of sines and solve that triangle? And so I've actually got that scenario created here, and then I'll explain what it means by ambiguous here in a minute. All right, so I'm going to draw my triangle out, and I'm going to just kind of refer to my own plans here so I can make sure I sketch this how I want to. Now, this is essentially going to act as the horizontal. Now I'm going to put A here at this vertex, and I'm going to measure this out. I'm going to label it a little bit different than what we did before. So this is going to mark 43 degrees for angle A. I'm going to actually put angle C at the top, and I'm going to put angle B down here in the bottom corner. And the reason why I'm writing it like this is because then this would tell me that this is 24. And then the opposite from A is 18. So this has to be fixed somewhere and swing down. So let's just say this is 18, like this. And I might actually, let's make it a little bit shorter. This is 24. So we'll say right there. All right, so this will be 18. And B then is right here given by that corner. All right, and so notice I don't know little c, I don't know angle B, and I don't know angle C. But you'll see this in the directions. I can find angle B using law of sines. And the reason why I can go through and find this missing angle is because I know angle A, I know side A, and I know side B, right? So the only unknown, if I'm setting up my law of sines then, would be that angle, and we can go through and solve for it. So I'm going to set up my law of sines here, where I have sine of angle A over little a, which is 18. This is equal to sine of B, which I don't know yet, divided by its side, which would be 24. Now, because I'm solving for B here, I need to get sine of B by itself first. So I'm only going to cross multiply in one direction. So I'm only going to bring the 24 over. So I get 24 sine of 43 degrees divided by 18 is equal to sine of B. Now, to make sure that you've got everything right in your calculator, I am going to go ahead and figure out what this decimal is. This comes out to be roughly 0.909331147. This decimal is equal to sine of B. Because we've talked about in the inverse trig section back in the previous mod that if I'm solving for an angle, in particular sine of an angle is equal to something, if that equal, what I'm setting this equal to is not on the unit circle, then the way that I'm going to solve this is to use a calculator and to take inverse sine. All right, so I'm going to hit second sine in the calculator and take second sine of 0.909331147. This is going to give me angle B because I'm undoing sine, right? I'm getting rid of it. When you do that in a calculator, you should find that angle B is roughly 65.4 degrees. Let's just go ahead and say 65 flat. So this means that if B is 65, because I know A, we can find angle C, right? Angle C has to be 180 minus 43 minus 65. So angle C has to be roughly, let's see, 180 minus 43 is 137 minus 65, so 72. And that makes sense, but roughly based off of my picture that I have. Now that I have angle C, we can go through and find side C using law of sines. So this becomes very familiar in terms of the previous examples. So sine of 43 divided by 18, again using that given numbers that haven't been rounded. Sine of 72 all over side C. Cross multiply. It's equal to 18 sine of 72. And then C is going to be equal to, when I divide by sine of 43, you should get 25. I'm just going to round to the nearest whole number here. And so this would give me the measurements for the triangle that I essentially have sketched for you here. Now, here is where and why this is called the ambiguous case. When we went through and we found that sine of B is equal to this decimal 0.909331147, right? The whole reason that I'm essentially putting this down is remember what this is asking me to do. Right, what this is telling me to do is to find an angle that when I take the sine of it, I get this positive number. All right, well, think back to a unit circle and ask yourself in which quadrants will sine ever be equal to a positive number? Well, hopefully you're recalling that that happens here in quadrant 1 and it happens here in quadrant 2. And in both cases, if I was to go an angle here, the sine value would be the exact same if I was to go to the same reference in the second quadrant, meaning that there are always two answers where sine can be the same value, right? It can be either something less than 90 or it can be something greater than 90. So when we go through and we do inverse sine in the calculator here and we get 65.4 or 65 degrees, we are only finding the first quadrant answer that would solve this original problem. There is a second answer that we have to take into account. Thus, the name ambiguous case, right? Ambiguous means unknown, right? Based on the information, we're not sure what exactly we may have. Because in the ambiguous case, there are three results that can happen. Under the given information, you can either have one triangle, like what we just got here. Because there are two possibilities for B, that means there could be two possible triangles that you can draw. Or, and going through and even trying to set this up under the given information, you might not be able to get any triangle. And that essentially gives you the third type of case here. Now, to help show you why there is a chance here for two possible triangles, and to hopefully give a little bit more concrete to this, let me take this picture again that we drew here for my triangle. And again, if we were in class, I would have been able to actually measure this out. In past classes, what I've done is essentially taken a ruler and kind of showed this. And I kind of alluded to it a second ago that when I'm drawing C here and I have this connection, C is not fixed, right? This angle, meaning that when I measure this out to be 18, this just needs to be 18 and then intersect somewhere else on this horizontal. Another place that it could intersect would be something like this. So if that's the case, right, if I can draw another side for A here that's 18 but closer, right, C gets smaller, so it's almost like a swing, then I've essentially created another possible triangle under the given piece of information. This one that is super, super skinny. Right, so I'm going to re-sketch this with the very, very skinny triangle. And I'm going to try to exaggerate it, kind of make it a little bit bigger. Because this is going to be my new C, and this is my new B. Notice how B now is greater than 90 degrees. It's creating an obtuse. And remember that the second possible angle can be in quadrant 2, which is greater than 90 degrees. Angle A, again, was 43. Side B was 24. That piece was fixed. Right? And side A here is 18. Well, how do we figure out what this other possible answer is? Well, where that other answer actually comes from, remember, is that if I know the first quadrant number here, then that is the reference for any other triangle in any other quadrant, meaning that that's 65 degrees. What I need to do is take that away from 180. I need to find its complement, right? Or excuse me, its supplement, all right? I need to find its supplement. So what I'm going to do to find my other possible angle for B is I'm going to subtract 65 from 180. So I get another possible result would be 115. Now what I want you to do is in your calculator, actually do sine of 115. And I want you to look at your answer because your answer should look very, very familiar if you do. Right? When you do sine of 115, and here I'll do this in my calculator as well, so I'm not just making it up as we go. If I do sine of 115, I get 0.9063007787. Now remember that 65 was rounded, so 115 is rounded, but I'm getting roughly 0.906, which is really, really close to this initial decimal that we got before. All right, so I just want to double check. Divided by 18. So we are not super far off. If I was to do 65.4 instead, then this would be 115, 114.6. So maybe sine of 114.6 would be closer. And I get 0.909. So you can see how just rounding it, how much of my answer is kind of thrown off here. But the fact of the matter is that 115 is another solution, approximately another solution to this equation, right? When I go through and do an inverse. To hopefully, again, show the impact of that inverse trig video in the previous mod, it's that when you do inverse sine in a calculator, there are always two answers, but the calculator can only give me one. All right, when the calculator gives me that single answer, I need to use that to find any other answer or any other possible answer. In this case here, it has to be greater than 90, aka it's in quadrant 2. So I'm always going to subtract that first angle for B from 180 to get my other possibility. Now the reason why I keep saying just another possibility is we just need to make sure that even 115 works, right? So angle A has to be 43. So if I'm going to go through and find this other possibility for C, I need to make sure that these angles combined are less than 180 so C could even exist, right? So if I do 180 minus 43 minus 115, notice this is going to come fairly close because 180 minus 43 again is 137 minus 115 is 22. So I get another possibility for C here, which is 22 degrees, which means I also have another possibility for little c, which I'm going to call little c2. To find little c2, we can use law of sines. Again, I want to use given information, so sine of 43 degrees over 18 is equal to sine of 22 degrees over little c2. And then I'm going to cross multiply and solve. When you do that cross multiplication and divide, you should get little c is roughly 10.06. We could say 10 in terms of my rounded final answer. So this is a scenario where just setting up angle A, side A, and B being 24, we can actually create two different triangles that fit this description, right? And it, again, it is based off of this idea that this side is fixed, this angle is fixed with the horizontal, but the distance along the horizontal and the angle up here, if you think about it like a swing, are not fixed. So this can open and close. This acts like it's on a hinge, where I just need to see where the door is going to hit the ground. And the door can hit the ground here, and it can also hit the ground here. If you think about it like an equilateral triangle, how that can work. All right, and so I've got another example here to help illustrate this ambiguous case, and there's some practice problems to kind of go along with this. But essentially the idea here is to determine how many possible triangles can even be formed under the given sketches that I've shown you. So as of right now, it looks like we have at least one triangle, all right, but we need to make sure even that works. All right, so let's look at part A here. So we're given angle A, which is 38. We're given side A, which is 24, so it's similar. We don't know angle B, but I do know its side. I don't know angle C, and I don't know its side. So the only thing I can really do here is, using law of sines, solve for the missing angle. All right, so I'm going to go through and say sine of 38 over 24 is equal to sine of B over 6. I'm going to cross multiply the 6 over, divide by 24. This is going to give me sine of B. Now that decimal, to make sure that we're going along the right track, is 0.153915. And again, sine of my angle, there are two possible angles that can give me this positive number. All right, the first answer can be given to me by using the calculator and doing inverse sine. We always find the first answer by doing this. So this is going to tell me that angle B is approximately, I have 8.85, which I'm going to say is 9 degrees. So there's my B. Right, so B exists, so that means I have at least one triangle. So from here, I can go through and find C, right? I know that out of 180, A is 38, and B is 9. So this would give me an answer of 133 for my angle C. So there's my angle for C. And now I can use this to go through and find my little c. So I can find little c by doing sine of 38 over 24, again using the given information, sine of 133 degrees, and divided by little c. Now cross multiplying and dividing, you'll get c is approximately 28.5. I'll save the work in between for you as an exercise. And so this would give me the information that I would need for at least one triangle. right? I have angle B, side C, and angle C. So now let's look at if another possible triangle would work. Now all of this again stems from my first answer for B and from this equation here as a consequence of that. All right, so if angle B is 9, that means the other possible answer for B, so I'll call this B2, has to be its supplement. So subtracting that from 180, I would get that the other number that would work for B would be 171. And again, you can check that. If you did sine of 171 in your calculator, you'll get a decimal very, very, very close to 0.153115, depending on how you rounded with that decimal and are rounding in terms of the angle for 9 degrees. But you should get something very, very close. Now, if that's my angle for B, remember that angle A is fixed at 38, and you should already see what the issue is in terms of trying to even go through and find out what C could be, right? Because 38 and 171 is already greater than 180 degrees, meaning that if I let B be this other possible angle, then I do not have another triangle, right? This is a scenario where there is only one possible triangle that can be drawn. And so it is this equation here that actually tells me if I'm going to have one triangle, two triangles, or none, based off of finding that second angle and seeing if it works. Now, if the first angle doesn't even work, if I can't even get an answer for B, then that results in no triangles that can be possibly drawn. Okay, so I don't have an example of that because there's not anything unique about it. You're setting the problem up like normal, and you'll see when the calculator gives you an error, what that is implying is no triangle. Instead, I want to spend time looking at one more two triangle case, which is what B is going to showcase. Okay, so in part B, I'm given these numbers and given these measurements where I know angle C and side B. So that means I can use law of sines to find angle B again. So sine of 42 over 92 is equal to sine of B over 120. I'm going to cross multiply, so I'm going to bring the 120 over. So 120 sine of 42 divided by 92 is equal to sine of B. Again, doing inverse sine of this, you should get that you're doing the inverse sine of this decimal, so 872,779. And I'm going to take the inverse sine to give me that angle B is approximately 61 degrees. Now, if B is 61 and C is 42, this means that angle A has to be approximately 77 degrees. And using this, we can now find little a by setting up, again, our given, sine of 42 over 92 is equal to sine of 77 over little a. And then cross multiplying and dividing, we'll get that little a is approximately 134. Now, this is all just the information for the first triangle. We need to see if a second triangle exists that could solve for angle B and give me sine of that angle to be at 0.872779, right? Another one where this ratio would hold to be true. Now, to find it again, I'm finding the supplement of 61. So I'm going to take 61 from 180. So I get a possible angle of 109 degrees, or 119 because I can't subtract apparently. And so I want to see it. Does this work for a second possible angle for B? Now, remember that angle C was 42 and it has to be 42. So notice by adding these two things together, we do get an angle. There can be a result for angle A, right? So I'm going to call this A2. I'll draw a line to separate it. Try to really exaggerate it. So A2, if I do 180 minus 119 minus 142, I get the second possible for angle A would be 19 degrees. So notice how A is a lot smaller than what we found in the first part. And then I'm going to use law of sines with sine of 42 over 92 equal to sine of 19 over little a. Now this little a will represent little a2, and I'll cross multiply and divide to get little a2 is approximately 45. So I get two possible triangles here. Now the given information again is fixed. The numbers that I can actually change and manipulate would be angle A, side A, and little angle B, which is what we're finding here. So I get B1, A1, little a1, B2, a2 and little a2 in terms of the second possible results here. Okay, so this is the ambiguous case for triangles. And this only occurs when we have a law of sines. Now, there are two types of triangles that law of sines cannot solve. In other words, we're given a combination and I cannot ever pair up an angle with its opposite side. Excuse me. And that is cases where I want to use what's called the law of cosines. Now, those two cases are specifically side, angle, side, and then side, side, side. Right? And both of these cases, we would be able to draw unique triangles. There would be no other way to come up with another possible triangle. Thus, there's no ambiguous case when you have a law of cosine type issue. All right, so if I have side, angle, side, then that means I'm going to use law of cosines. Law of cosines is a little bit more complex. It is a squared is equal to b squared plus c squared minus 2bc cosine of angle A. And then there are two more equations, but they are very, very similar. It follows a pattern. B squared is equal to a squared plus c squared. Notice it's the other two. Minus 2ac, those two. And then cosine of what I'm solving for, but it's angle. C squared is a squared plus b squared minus 2ab cosine of angle C. Notice this format right here is very, very similar to Pythagorean. What it says is that if I have a non-right triangle, I actually have to subtract this extra little piece here from Pythagorean for it to be true. Okay, so these three equations here make up what is known as the law of cosines. Notice it only involves having to know one angle, and then I would need to know two of the sides, thus the side, angle, side, or I would need to know all of the lowercase sides here in order to find my missing capital letter, thus side, side, side. Right? I cannot solve an angle, angle, angle problem. It is impossible because an angle, angle, angle problem can be any size triangle. So let me show you an example here. We'll use law of cosines, and this will round out the video. All right, so I've solved the triangle, drawn there for A and repeated down here under the solutions. Notice this is a side, angle, side type problem. Right? I do not know lowercase a, and I do not know angle B or angle C. So the first thing that I'm going to do, and the only thing that I can find, is lowercase a. So I'm going to refer to my law of cosines, and I'm going to use the first equation here. I know that a squared has to be equal to b squared plus c squared minus 2bc cosine of angle A. Now I'm going to fill in what I know. So little b is 11, little c is 13, minus 2 times 11 times 13, cosine of my angle A, which is 43 degrees. Now be really, really careful as you're going through and calculating this. Now in a calculator, you can type all of this in as you see it and hit enter and get a number. In terms of practice, I would encourage you to look at this as two separate pieces. These pieces that are squared are going to result in one number. These multipliers in front of the cosine are going to result in another number that have to remain completely separate. Right? So when I go through and do 11 squared plus 13 squared, you should get, let's see, I want to pull up the number. I actually went through and just did all of it. So 11 squared is 121, 13 squared is 169. So adding this together, you should get 290. Now this would be minus 2 times 11 times 13. 11 times 13 would be 143. Double that is 286. Cosine of 43 degrees. Now I would type this into the calculator. I would get a squared is equal to 80.8328, and then I would take a square root. And because the side of a triangle has to be positive, this would give me 8.99 approximately. And we could round this all the way to 9 and use that for A. Now we would need to find now angle B or angle C. Now because we know side A, you could say, well, let's go through and use law of sines. Now be careful, because when I'm using law of sines and I only know an angle, right, and I'm trying to find another angle, we can hit the ambiguous case. Now it is possible then that one of the two angles may work, and it's like, well, which angle is it? Because this triangle can only have one, given that we're starting out with a side angle side. So if you start with law of cosines, I'm going to encourage you to only use law of cosines. This means to find angle B, I'm going to use the law of cosines that has angle B in it, which is the second one, which has B squared is equal to A squared plus C squared minus 2AC cosine of angle B. All right, so that way when I plug in everything that I know, B is 11 squared, A is 9, C is 13, minus 2 times 9 times 13 cosine of angle B. And this is what I was kind of saying earlier, Ron. I'll make sure I keep everything separate. So in other words, 11 squared is 121. Now I'm going to go through and find out what is this part, 9 squared plus 13 squared. When I do that, I get 81 plus 169 minus 2 times 9 times 13. So this is, let's see, 117 doubled is 130 or 234 cosine of angle B. Now I'm going to go through and add. So I get 121 is equal to 81 and 169. So that is 250 minus 234 cosine of angle B. Now these two things cannot combine because the 234 has a cosine attached. Excuse me. So what I need to do is actually subtract the 250 over first, and then I'm going to divide by negative 234. So I subtract by 250. This will give me negative 119, or 129, excuse me. This is equal to negative 234 cosine of angle B. I'll now divide by negative 234. And then I will take the inverse of cosine. So I'll do inverse cosine of 129 over 234. This will give me approximately 56.6 degrees, which we will just round up and say 57. So there's my answer for B. If I know B is 57, then I can find angle C because angle A, recall, was 43, if I remember right. So if B is 57, that's equal to 100. So angle C has to be 80 degrees, approximately. And there we found all the missing pieces of information. In the lesson plans, I actually went through and used law of sines. So if you want to see what that would look like, feel free to go through and do that. Just remember you would have to kind of double check and see if another possible angle can work. I would get 123.4 is the other answer for B, like the other possibility. And if that's true, 123, notice I can add that to A and actually get another angle for C. But that's not going to work because of the information, again, we have. The ratios won't hold to be true. So I'd actually ask you not to do what I did in the lesson plan. That's posted on PowerSchool Learning where I use law of sines. Always kind of tend to use law of cosines again. And that's actually what I do in part B. So let's take a look. This will be the final one, if I remember right. Yo. All right, so let's look at triangle, the second triangle here. Now, excuse me, I've been talking for so long. Notice how I know all of the sides, but I don't know any of the angles. So I'm going to use law of cosines twice to find two angles. Here, let's find A and B. And then once I know two angles, we can subtract from 180 to find C. All right, so let's go through and find angle A first. So I'm going to use the A squared form. My throat is so dry. I don't have any water. All right, so A is 17.75. B is 17. C is 11.62. And again, filling those in. Okay, using the calculator, minus 395. Okay. Whew. Hopefully, again, do not combine these two things. I'm going to subtract over the 424 first. This will give me negative 108.9619. And then negative 395.08. Dividing by negative 395 and then taking the inverse cosine, you should get angle A is approximately 74. I'm going to encourage you, go through and find angle B kind of as an exercise. I won't kind of walk through that because it's kind of busy work at this point. You can see the work laid out in the lesson plan. Angle B is approximately 67 degrees, which means that angle C would have to be approximately 39. The approximations, again, because we rounded with the decimals earlier. But these are the measurements that would work for this triangle and solve it. So make sure to take a look at the project assessment. You'll see in some of the practice problems some examples with the applications here, like why these laws are so important and why we look at them. But also, more importantly, their connection to vectors, because they can actually help solve some vector problems in physics and in a lot of other applications. So I'd encourage you to do that. I apologize about the coughing and my voice getting really raspy. I'm sure that if you're listening in on headphones, I probably just made you go deaf. So I'm really sorry about that. I'll try to turn it down when I'm editing the video later. So if you didn't hear anything, then that's probably why. Movie magic. Otherwise, thank you for watching. If you have any questions over the laws, let me know. Hopefully most of this was review. I know the ambiguous case can be kind of tricky, so definitely come during virtual class times or Monday or during office hours to get some extra help with that, because I'd love to help you through that. So have a great day, and again, thank you for watching.